Assalamu alaikum. Let's start our lecture. After FSK, we have PSK, that is phase shift keying. Uh, it is another form of angle modulation, where the amplitude of the modulated signal will remain constant. And it is an M array digital modulation scheme, similar to conventional phase modulation, except with PSK. The input is a binary digital signal, and there are limited number of output phases possible. So in PM modulation, phase modulation, that is analog modulation, where the output of that will be a continuous analog signal, whereas here the modulated signal, that is the output, will be in the binary form, binary signal, zeros based on consist on zeros and ones. Input is also digital, whereas in analog modulation, input is analog. So based on the input, we say analog modulation or digital modulation. If the signal input is analog, modulation will be analog. If the signal input is digital, then this we have the digital modulation. So here in PSK, the input binary information is encoded into groups of bits before modulating the carrier. So because it's an M array, so we have to form the symbols. Symbols will be consist on the bits. So simplest form is BPSK, where you have 1 bit per symbol. But we can have more than 1 bit in a symbol. So if that's so, then we need to form the groups of bits before modulating the carrier. The number of bits in a group ranges from 1 to 12 or more. As the number of bits in a group increases, the distance between the neighboring symbols, distance between the symbols will reduce. That will lead to higher bit error rate. So we have to choose this number of bits in a group very carefully, based on our requirement of data rate and the tolerance of the bit error rate of the system. The number of output phases is defined by M, as described in equation 6, that is 2 power n is equal to m, where n is the number of bits in a group. So that is capital N. 2 power n is equal to m. So total number of phases will depend on how many bits we take in a symbol. If we take one symbol, 1 bit per symbol, then this will be 2 power 1 and is equal to 2. Then we will have two phases, 0 and 180. If we have 2 bits per symbol, then this will be 2 power 2 is equal to 4 phases. Can be 0, 90, 180, 235, and 360. Two 70 and 360. So the simplest form of PSK is binary phase shift keying, that is PSK, where n is equal to 1 and m is equal to 2. Therefore, with BPSK, two phases are possible for the carrier. One phase represents a logic 1 and the other phase represents a logic 0. As the input digital signal changes state, that is from a 1 to a 0 or from a 0 to a 1, the phase of the output carrier shifts between two angles that are separated by 180 degrees. So this is done by dividing 360 by 2. That will give you the separation between the two possible outcomes, 0 or 1. So the separation is 180 and we keep there one is at 0 and another one is at 180. But you can use any degrees, but the difference between the two outputs should be by 180. Hence, other names for BPSK are phase reversal keying and biphase modulation. As see, you can see the 0 is opposite of 180 and vice versa. So it's another name reflect that phase reversal keying and biphase modulation. We are modulating on only two phases. So that's why another name is biphase modulation. And it's a form of square wave modulation of a continuous wave signal. Square wave means आपकी जो zeros and ones होते हैं, they kind of form a square wave. So that's why it's a square wave continuous wave signal. So there is no break in the signal because continuous wave, if you move from 0 to 180 and 180 to 0. Figure 12 shows the BPSK transmitter, a simplified block diagram of a BPSK transmitter that uses the balanced modulator as a phase reversing switch. So here it is, this balanced modulator. You can see we have level converter that convert unipolar signal to bipolar signal. So the binary data only consists on no voltage, that is 0, and one positive voltage. So this level converter convert this unipolar signal that has only one polarity into two polarity or bipolar signal, where binary 1 and 0 will be represented by plus and minus voltages. Then we have balanced modulator where we have the carrier oscillator, reference carrier oscillator, that is sin omega ct in this case. So that will be multiplied with positive voltage or negative voltage. If we say it's +1, and -1, then the output of the balanced modulator will be plus sin omega ct or minus sin omega ct. Then this will pass through a band pass filter. Only particular frequencies will be passed, others will be blocked. And the output will be modulated PSK filter. So depending on the logic condition of the digital input, the carrier is transferred to the output either in phase or 180 degrees out of phase with the reference carrier oscillator. See, it is either plus sin omega ct means it is in phase with the reference oscillator. Minus sin omega ct means it is 180 degrees out of phase with respect to the reference oscillator. Figure 13 shows the schematic diagram of a balanced ring modulator. The balanced modulator has two inputs, a carrier that is in phase with the reference oscillator and the binary digital data. For the balanced modulator to operate properly, the digital input voltage must be much greater than the peak carrier voltage. This ensures that the digital input controls the on-off state of the diodes. That is D1 to D4. Let's see first figure 13. So this is figure 13. That is balanced ring modulator. A is that, B is logic 1 input, and C is logic 0 output. So this one is balanced modulator, balanced ring modulator, where you can see 4 diodes, D1, D2, D3, and D4. And when the input is logic 1, D1 and D2 diodes will be forward biased. And the input voltage should be greater than the peak voltage of or the operating voltage of D1 and D2, or these simply the diodes, so that they can be forward biased. And you see, when we have logic 1 input, the input carrier and the output signal are in phase. Whereas when we provide logic 0 input, the input carrier input is uh, out of phase or 180 degrees shift in its angle with respect to reference carrier at the output. So that discussion is in the slide, previous slide 47. That says that if the binary input is a logic 1, positive voltage diodes D1 and D2 are forward bias and on, while diodes D3 and D4 are reverse bias and off. With the polarities shown, the carrier voltage is developed across transformer T2 in phase with carrier voltage across T1. Consequently, the output voltage is in phase with the reference oscillator that is also shown in figure 13B in this figure. And 13C displays that if the binary input is a logic 0, that is negative voltage, diodes D1 and D2 are reverse biased and off, while diodes D3 and D4 are forward biased and on. That you can see in figure 13C. As a result, the carrier voltage is developed across the transformer T2. That is 180 degrees out of phase with respect to carrier voltage across T1. Consequently, the output voltage is 180 degrees out of phase with the reference oscillator. Then we have figure 14 that shows the truth table phasor diagram and the constellation diagram of a BPSK modulator. So here it is, you can see logic 0, the carrier will be modulated to 180 degrees and logic 1 carrier will be modulated to 0 degrees. So for zeros and ones, the carrier will be shifting between these two phases. This one is a phasor diagram. You can see logic 1 at 0 and logic 0 is at 180 degrees. So, and this one is the constellation diagram where you can see two angles and their respective logics. Constellation diagram, which is sometimes called a signal state space diagram, is similar to a phasor diagram, except that the entire phasor is not drawn. So in a constellation diagram, only the relative positions of the peaks of the phasors are shown. Bandwidths of BPSK. Balanced modulator is a product modulator actually, where you can see the input voltage is multiplied with the reference carrier that has two possibilities, plus sin omega CT or minus sin omega CT. One output will be in phase and another out can be in the out phase. If it is logic 1, then it is 0 degrees change in the phase of the carrier. If it is minus sin omega CT, that is 0 logic, then it is 180 degrees change in the phase with respect to the reference carrier. So in a BPSK modulator, the carrier input voltage is multiplied by the binary data. If 1 volt is assigned to a logic 1 and 1 volt is assigned to a logic 0. So this is a typo error. This is not 1 volt. This is minus 1 volt. And minus 1 volt is assigned to a logic 0. The input carrier sin omega CT is multiplied by either a plus or minus 1. That is plus sin omega CT in case of logic 1 and minus sin omega CT in case of logic 0. Consequently, the output signal is either plus sin omega CT or minus sin omega CT. Again, minus is missing here. Another typo is here. The first represents a signal that is in phase with the reference oscillator, and the later a signal that is 180 degrees out of phase with reference oscillator. Each time the input logic condition changes, the output phase also changes. Consequently, the BPSK, the output rate of change, that is baud, is equal to the input rate of change, because every symbol will have only one bit. So in this case, baud and bit rate will be same. And the widest output bandwidth occurs when the input binary data are at alternating 1 and 0 sequence. Yeah, that is a worst case. If you have the alternate 1 and 0, in that case, the bandwidth required will be the maximum. So frequency of an alternative 10 bit sequence is equal to 1/2 of the bit rate. That is f of a is equal to fb by 2. So the BPSK output is equal to sine 2 pi f of at into sine 2 pi f of ct. So this is the modulating signal and this is the carrier. So f of a is equal to maximum fundamental frequency of the binary input in hertz, and f of c is the carrier reference carrier frequency in hertz. So solving this trigonometry identity for the product of two sine functions, so we can apply a half angle of the so this can be seen as a part of a part of the formula cos alpha minus beta. In that you will have the second part, you will find sine alpha and sine beta. So we can replace this one with the half cosine angles of alpha and beta. So that read as 1/2 cos 2 pi fc minus f of a. That is alpha minus beta, and this is alpha plus beta. So in that, the Nyquist double-sided bandwidth B is 2 of f of a, and because f of a is equal to by 2, where fb is input bit, so the bandwidth will be equal to the bit rate. Same. So the bandwidth, bit rate, and the baud rate for PPSK is same, where B is the minimum double-sided Nyquist bandwidth. So here it is, you can see binary phase shifting with alternative 1 and 0. When we need the highest bandwidth, you can see if it is 1, and then it's starting from 0 degrees. When it is 0, it is 180 degrees. Again, 1, 0, again 0, 180. So kind of going to show that 0, 180, 0, 180, 0, 180. So that is an example 4. You can do it. Figure 16 shows the BPSK receiver. Shows the block diagram of a BPSK receiver. The input signal may be plus sine omega ct or minus sine omega ct. The coherent carrier recovery circuit detects the regenerates a carrier signal that is both frequency and phase coherent with the original transfer carrier. Let's see first the diagram. You can see the input can be either plus sine omega ct or minus sine omega ct. Pass through the band pass filter. All high frequencies will be passed. All low frequencies, that is f of a, will be blocked here. Only carrier frequency will be allowed to pass. This is the coherent carrier recovery. Carrier will be recovered from the signal. So it is consist on the sine omega ct, that is the carrier. So that will be multiplied with plus sine omega ct and sine omega ct. So the output of the balanced modular will be sine square omega ct. That will be again passed through the low pass filter, not the band pass filter, but the low pass filter means carrier will be blocked here. Only the logic will be allowed to pass. Then again we have the clock recovery, and then we have the level converter, and that will convert the unipolar binary bipolar to unipolar data output. So that operation is something like this: sine square omega ct when passed through the low pass filter. So sine square omega ct can be written as 1/2 1 minus cos 2 omega ct. So this twice of the omega ct frequency we cannot pass through the low pass filter. So this will be blocked or will be filtered out. The only remaining thing we will have the 1/2. So 1/2, that is output, that is plus 1/2, that is logic 1. Because it's plus 1/2, so that it will be logic 1. So the low pass filter has a cutoff frequency much lower than the twice omega c, and thus blocks the second harmonic of the carrier and passes only the positive constant component, a positive voltage difference, demodulated logic 1. So the balanced modulator is a product detector. The output is the product of two inputs, the PPSK signal and the recovered carrier. The low pass filter separates the recover recover binary data from the complex demodulated signal. Mathematically, the demodulation process is as follows. So then we just uh, did that. If we receive logic 0, then the output is minus sine square omega ct. That will be equal to minus 1 over 2, 1 minus cos 2 omega ct. So this component will be filtered out through low pass filter. So it will not be there. The only thing that we will have this minus 1 over 2, that will be equal to logic 0. The LPF has a cutoff frequency much lower than 2 mega C, thus blocks the second harmonic of the carrier. So that's conclude this lecture. If you have any questions from this lecture, you can ask. After BPSK, we have QPSK, that is quaternary phase shifting. Quaternary here represents 4 phases, means shift in the modulated or the in the carrier signal in 4 phases. So the information can change in any one of the phases. So QPSK or quadrature PSK, as it is sometimes called, is another form of angle modulated constant amplitude digital modulation. Is an M array encoding scheme where n is equal to 2 and m is equal to 4. That is, we have now 2 bits per symbol or 2 bits per group. That means at a time we will take 2 bits instead of 1. And so that there now will be 4 output possibilities when we take 2 bits like 0, 0, 0, 1, 1, 0, and double 1. So that's why the name is quaternary, meaning 4. With QPSK, 4 output phases are possible for a single carrier frequency. Because there are 4 output phases, there must be 4 different input conditions. So there will be 4 different input conditions and 4 different output phases. Because the digital input to a QPSK modulator is a binary based 2 signal, to produce 4 different input combinations, the modulator requires more than a single input bit to determine the output condition. So with 2 bits, there are 4 possible conditions. Therefore, with QPSK, the binary input data are combined into groups of 2 bits called die-bits. And in the modulator, each die-bit code generates one of the 4 possible output phases. Plus 45 or plus 135, minus 45 or minus 135. Therefore, for each 2 bits, die bits logged into the modulator, a single output change occurs and the rate of change and the output is equal to 1/2 the input bit rate. That is, 2 input bits produce 1 output phase change. A block diagram of a QPSK modulator is shown in figure 17. Let's see that diagram first. That you can see here, we have binary input data. Its bit rate is f of b, and we have bit splitter. So the total input rate is f of b. Our total input data is f of b. So that will be divided into 2 equally, fb by 2 and fb by 2 into 2 channels, I channel and Q channel. I channel is I for in phase channel and Q channel, that is quadrature channel. As you can see, one is multiplied in the ballast modulator, that is the product modulator basically, with sine omega ct, and another component that is Q channel, that we say the quadrature, that is 90 degrees phase shift. After 90 degrees phase shift, we have sine into cos omega ct. So Q channel will be multiplied with the quadrature component of the sine omega ct, that is cos omega ct. So the two outputs of the balanced modulator can be plus minus sine omega ct in the I channel, and in Q channel it will be plus minus cos omega ct. So they will be passed through band pass filter, and that means omega c will be passed through, other low frequency will be blocked. So linear summer, and then the output of this band pass filter, same band pass filter as of this job is to only pass omega c, frequencies less than that will be blocked. So the output will be plus minus sine omega ct and plus minus cos omega c. So the binary input can be 0 0 1 0 1 1 or 1 0. So one bit will go to I channel and one bit go to Q channel, and based on that, we will choose a output here based on the received plus minus. So that is also mentioned here, the same thing that I described with respect to figure, with the help of the figure is mentioned in this slide. So for the QPSK modulator shown in figure 17, construct the truth table, phasor diagram, and constellation diagram. So the solution is for a binary data input, when we have Q is equal to 0 as well as I is equal to 0, the two inputs of the I balance modulator are minus sine omega ct and minus cos omega ct. That is, the total output will be minus cos omega ct and minus sine omega ct. So that you can see it is equal to 1.414 sine omega ct minus 135 degrees. So does anyone has idea how we do it? ये कैसे हुआ? From minus cos omega ct and minus sin omega ct equal to 1.414 sin omega ct minus 135 degrees. With section 2, I did this in the class, if you will recall. So if you know how to do it, then we move ahead. Is I will explain it on the whiteboard available in Teams. Okay, anyone knows how to solve this one? Minus cos omega ct minus sin omega ct. How this quantity equal to 1.414 sin omega ct minus 135. Anyone? So what we did here, we write this quantity minus cos omega ct minus sin omega ct is equal 1.414 sin omega ct minus 135. So this we have to uh, show that from this quantity we can go to here. So for that we say that uh, we are in the third quadrant where both are negative. So we put here sin 135 and sin 135. Basically, that is the second quadrant. And cos omega ct minus cos 135, cos 135, and sin omega ct. So, and we know that sin 135 is equal to 1 over square root 2, and cos 135 is equal to minus 1 over square root. So we can write this equation as minus is there, sin 135 is also there, and this is 0.707, and cos omega ct and minus again here that will be cos 135 and 0.707. But this will be minus. This will be minus 0.707. Cos 135 is, and along with it we have sin omega ct. So we can take this common, that is 1 divided by 0.707 can be taken as common, and the remaining thing that we can write as minus m minus sin omega ct and cos omega ct, and this minus can be minus, minus will be plus, so this will be plus, and we have here cos omega ct and sin omega ct. And this, when you divide 1 divided by 0.707, that is 1 divided by square root 2, that will be equal to 1.414. So instead of this, we can write 1.414. That is same here. And we can rewrite this one as, sorry, cos 135. And this is sin 135. So alpha is omega ct. So we write down in that form sin alpha, sin omega ct, and beta is 135 cos 135. Then minus sin beta is 135, and then cos alpha, that is omega ct. So this will be 1.411, and this can be written in the form of alpha and beta. So in alpha beta formula, this minus sign will be same as in the equation here. So that will be same. This minus sign and this minus sign will be in same, where it is reverse in cos alpha and beta formula. So here it is sin alpha, alpha is omega c, T minus beta is 135. So this is how we convert a quantity given as minus cos omega ct minus sin omega ct to 1.411 sin omega ct, where 1.411 is the amplitude and this is the phase shift in the carrier. Carrier is sin omega ct, the reference. So we will change its angle by 135 and its amplitude is 1.411. Okay, is it clear? So this is we done on the whiteboard. Now I will ask you to do it for q is equal to 1 and I is equal to 1. In that case, instead of minus, we will have both quantities in positive plus cos omega ct and plus sin omega ct. Then what will be that equal to? So using the same way, you can do it. Both are positive. So please try to solve this one. Uh, I give you like 10 minutes to do it. Okay. In this example, q is 0 and r is equal to 0. I want you to solve this same as we did on the whiteboard for q is equal to 1 and I is equal to 1, and you have exactly 10 minutes. Okay. I will see you after 10 minutes. So figure 17 shows the construct truth table phasor diagram and the constellation diagram. So that one's the truth table, and this one is the phasor diagram, and this one is the constellation diagram. As you can see, for the two inputs as 0, 0, the output phase of the carrier will be minus 135, and for 0, 1 it is minus 45. For 1, 0 it is plus 135, and plus and 1, 1 for it is plus 45. Figure B and C uh, can be seen that QPSK, each of the four possible output phasors has exactly the same amplitude. Therefore, the binary information must be encoded entirely in the phase of the output signal. So that was in the previous figure where you can see the amplitude of all the different inputs are same. This constant amplitude characteristic is the most important characteristic of PSK that distinguishes it from QAM, which is explained later. Also from figure 18b, it can be seen that the angular separation between any two adjacent phasors in QPSK is 90 degrees. Therefore, a QPSK signal can undergo almost a 45 degrees or 45 degrees shift in phase during transmission and still remain the correct encoded information when demodulated at the receiver. Figure 19 shows the output phase versus time relationship for a QPSK transmitter. Bandwidth considerations of QPSK. With QPSK, as the input data are divided into two channels, the bit rate in either of the I or Q channel is equal to one half of the input data rate. Consequently, the highest fundamental frequency present at the data input to the I or Q or the Q balance modulator is equal to the 1/4 of the input data rate. As a result, the output of the I and Q balance modulator requires a minimum double-sided Nyquist bandwidth equal to one half of the incoming bit rate. Thus, with QPSK, a bandwidth compression is realized. Also, because the QPSK output signal does not change phase until two bits have been clocked into the bit splitter. The fastest output rate of change is also equal to one half of the input bit rate. As with BPSK, the minimum bandwidth and the baud rate are equal. This relationship is shown in figure 20. So you can see in figure 20 that the worst case input condition to the IRQ balance modulator is an alternative 1 and 0 pattern, which occurs when the binary input data have 1100 repetitive patterns. One cycle of the fastest binary transition, a 1-0 sequence, and INQ takes the same time as four input data bits. Consequently, the highest fundamental frequency at the input and fastest rate of change at the output of the balance modulator is equal to 1/4 of the binary input bit. That means the bandwidth requirement of QPSK is half to that of the BPSK, because here we are transmitting two bits uh, in one symbol. So the rate of change in the I and Q channel will be half of to that of the input bit rate. So the output of the ballast modulators can be expressed as, where you can see sine omega AT, sine omega CT, where omega AT will be equal to 2 pi f of B by 4t, and omega CT is equal to 2 pi FC. So the output will be 1/2 cos FC minus AP by 4. So this is the lowest bandwidth, this is highest bandwidth, and the total bandwidth will be equal to half of the bit rate. So that is the Nyquist minimum bandwidth. Then we have an example 6. Go through it. It has been solved here. Solved example. Then we have the QPSK receiver. The block diagram of a QPSK receiver is shown in figure 21. This one, where you can see we have the input signal. Input signal can be plus minus sine omega ct and plus minus cos omega ct. This particular case will be provided minus sine omega ct and plus cos omega ct. So this is power splitter, I channel and Q channel. So both will be multiplied with the carrier. One will be multiplied with sine omega ct and one will be multiplied with the cos omega ct. So this one is with the sine omega ct minus sine omega ct plus cos omega ct, and that is cos omega ct minus sine omega ct and cos omega ct. So there will be a low pass filter that will only pass through frequencies uh, below the omega c frequency, that is the carrier frequency, and there is only component. Those are the logic components that will be allowed, that you can see here. For I channel minus sine omega ct plus cos omega ct into sine omega ct. So when you multiply, this will be minus sine omega ct into sine omega ct, that is square, plus cos omega ct and sine omega ct. So this sine minus sine square omega ct can be written in the cosine form as minus 1 over 2, 1 minus cos 2 omega ct, plus this can be written in the half cosine angles, 1 over 2 sine omega c plus omega c, plus 1 over 2 sine omega c minus. So this component will be cancelled out, and this component will be twice of omega c, so that will be filtered out, same as this component will be filtered out. The only thing that remain is minus 1 over 2, that is logic 0. So the output for this input minus sine omega ct and cos omega ct is logic 0 from the I channel. So from I channel it is logic 0, and from Q channel it will be logic 1. So that will be 0 and 1. That will be the output of this QPSK receiver. So the power splitter directs the input QPSK signal to the I and Q product detectors and carrier recovery circuit. The carrier recovery circuit produces the original transmit carrier oscillator signal. The recovered carrier must be frequency and phase coherent with the transmitter reference carrier. The QPSK signal is demodulated in the I and Q product detector, which generate the original I and Q data bits. The output of the product detectors are fed to the bit combining circuit, where they are converted from parallel I and Q data channels to a single binary output data stream. Then we have offset QPSK. Is a modified form of QPSK where the bit waveforms on the I and Q channels are offset or shifted in phase from each other by 1/2 of a bit time. Figure 2020, figure 22 shows a offset keyed QPSK block diagram and the bit alignment and the constellation. Because changes in the I channel occur at the midpoints of the Q channel bits and vice versa, there is never more than a single bit change in the die-bit code, and therefore there is never more than a 90-degree shift in the output phase. In conventional QPSK, a change in the input die-bit from 00 to 11 or 01 to 10 causes a corresponding 180-degree shift in the output phase. So the advantage of QPSK is the limited phase shift that must be imparted during modulation. A disadvantage of QPSK is that changes in the output phase occur at twice the data rate in either I or Q channel. Consequently, with QPSK, the baud and minimum bandwidth are twice that of the conventional QPSK for a given transmission bit rate. Then we have at PSK. 3 bits are encoded, forming tri-bits and producing 8 different output phases. That means here we will have n3 and m is equal to 8, and there will be 8 possible phases rather than 4 that we have had in the QPSK with n is equal to 2 and m is equal to 4. So to encode 8 different phases, that means the incoming bits are encoded into groups of three. That will be 3 bits. That means we should have 3 channels. So it's called tri-bits. 8 PSK transmitter block diagram shown in figure 23. Where we have seen 3 channels Q, I, and C. C channel is like no chain channel or the common channel. C is for common channel. Same with the I and Q, except with Q it is inverted, with C it is straight. And you can see we have 2 to 4 level converter here. The PAM will be generated, and that PAM will be modulated with the product modulator, goes through the band pass filter, and we have the linear output. After the band pass filter, linear summer will pass through the band pass filter, and here we will have the 8 PSK output. That will be in the form of sine n. So here we have 2 voltage levels rather than one. You can see minus 1.307 and minus 0.541. So the incoming serial bit stream enters the bit filter where it is converted to a parallel 3 channel output. The I are in phase channel, the Q are the quadratic channel, and the C is not the common channel but is the control channel. So figure 23 shows the block diagram, whereas figure 24 shows you the truth table and the PAM levels. So an example is given here for a tri-bit input of Q as 0, I 0, and C 0. Determine the output phase for the 8 PSK modulator shown in figure 33. The inputs to the I channel 2 to 4 level converter are 0, 0. So from figure 4, the output is minus 0.541 volt. The input to the Q channel 2 to 4 level converter are 0 and 1. Again, from figure 24, the output is minus 1.307 volt. Thus, the two inputs to the I channel product modulator are minus 0.541 and sine omega ct. The output is minus 0.541 sine omega ct. Similarly, the Q channel output is minus 1.307 cos omega ct. When we combine them, that will be equal to minus 0.541 sine omega ct and minus 1.307 cos omega ct. Same can be solved through the same way as I shown you earlier, and that will be equal to 1.414 sine omega ct minus 112.5 degrees. For the remaining tri-bits, the procedure will remain same. For practice, you can take any of these combinations and try it at your home. So it's phasor diagram, time relation, and the output, and the truth table, and this is the constellation diagram. Bandwidth of this one will be 1/3 of the bit rate. So that is very clear. Now, as we have the 3 bits, we are talking 3 bits in a group per symbol. So the bandwidth will be 1/3 to that of the BPS code. So example is also there, receiver. So the output, the 8 PSK receiver is like shown it here. So that concludes this PSK. Similarly, we will have 16 PSK that we will see in the next lecture. If you have any questions till this slide, you can ask. So no questions. See you tomorrow, inshallah. Have a nice day. Allah Hafiz.